Hey, good morning. I'm Oliver Gao, Director of Cornell System Engineering Program. Today, we are so delighted and honored to have Professor Michael Kokkolaras and coming with us. Actually, he is a professor of mechanical engineering at McGill University, where he's also serving as Associate Dean for the Faculty Affairs at the Faculty of Engineering. So I think it's basically at Cornell, it's equivalent of our Associate Dean for Academic and Faculty Affairs. Yeah, so his research interest lies in the broad area of computational engineering, design, and also include multidisciplinary, derivative-free, and also and Bayesian optimization. So this will help multi-fidelity model management, digital twins, and also automated machine learning. So this is really, I think, a very nice combination of both, the traditional research area, but also all these emergent topics that are so important to our society. And also he looks at the requirements management, verification, validation, and also uncertainty quantification, because I know that, Michael, your work has a lot to do with decision making, and particularly decision making is not about decision making for the past. It's about decision making for the future, which is always full of uncertainty. So actually, if you're interested more about Michael's work and his honors, you can certainly visit his website. But here I just to mention, among all the other honors, he has received the ASME DED Design Automation Award, the University of Michigan College of Engineering Outstanding Research Scientist Award, and also the ASME Journal of Mechanical Design Editor's Choice Award. These are all very prestigious awards. So, Michael, welcome to Cornell, and thank you for taking up to visit us.
Thank you for the introduction, and thank you for having me. It's a privilege to be here, and I'm very glad to have this conversation with you.
Wonderful, thank you, Michael. When I was looking at your work, yesterday I visited your website to get myself prepared, and I'm so amazed about the work. And as I talked to you earlier, I feel you are really this system engineer, right? You're looking at the things, you're looking at the verification, validation, and all these aspects. So myself, and I believe many people who will be watching this video, they will be very curious to learn more. So Michael, how did your career evolve, and how did you come to this point where you are able to address all these important issues and with such a diversified but also each great combination of the knowledge? So we want to know more about you.
All right, so let me give you a brief introduction of myself. I was born and raised in Greece, in Athens, Greece, but I was German educated. I went to the German high school of Athens, which was a German public school embedded in Athens. So this was a direct pipeline to, back then, for me to study in Germany. And I went to the Technical University of Munich, where I studied aerospace engineering. And so at the time, I did not really, have any ambitions to go into graduate studies, but there was naturally an opportunity for me to come to the States and do a PhD. And I followed that opportunity without really having any plans. It was interesting how everything developed during my PhD. I was at the Rice University. And again, an opportunity presented itself to work with somebody who was really a very renowned professor in numerical optimization. That person, his name was John Dennis, and he was an applied mathematician, but I was an engineer. But John always wanted to collaborate with engineers in his career because he wanted to see the algorithms that he was developing being applied to engineering problems. And in fact, the unique thing in John's career was that he was extremely successful in both gradient-based optimization algorithms, but then also in derivative-free optimization algorithms. So, and that introduced me to the world of optimization. And as an engineer, I was always interested in understanding how our systems work, how the subsystems that comprise our systems interact, and sometimes also how systems themselves interact to create systems of systems. And it was fascinating for me to learn from early on that this is not the sum of the parts. You cannot just optimize every single component or every single system and then expect that it automatically translate to optimality at the system level or at the system of systems level. So that inspired my research in the area. And it was also at the time where the field of multidisciplinary optimization was born. It was in the early 90s. And multidisciplinary optimization was actually, it came to birth, it came to existence because people used optimization as a tool to help different teams and different disciplines coordinate their activities. In other words, the typical problem at the time was error elasticity. You had people looking at aerodynamics and people looking at structures, and the aerodynamicists wanted one design, and the structures engineers wanted another design. But the two interacted because there is a feedback loop between the two of them, and they couldn't really agree. So it was more or less the most dynamic personality would win, and they would get their design. But we wanted to introduce mathematical tools, optimization, to actually take care of this problem and give us what is the best compromise solution between two designs that need to address different, not just objectives, but disciplines. Anyway, so, and then, I applied all the time these techniques to try to improve performance of engineering systems, regardless of whether these are vehicles or aircraft or energy systems or any other type of mechanical engineering system that you can think of.
Wonderful. Thank you, Michael. So I think, of course, that was brief, but I think you mentioned, I think, several very important points. I think you mentioned John's work and how his work kind of, impacted, your career development, and also even, some of your interest, how your interest develops. And I think from there, you really talk about, and I feel one key thing is really that while, your training and also your advisor, the work, focus a lot on mathematics, but one thing I realized kind of, John and you have always emphasized collaboration and application, to the engineering field. And I think that's a very important thing. And also another thing I feel that you mentioned, you are not only trying to optimize the elements or not even the subsystem. You are actually, by considering the interactions among the subsystems and even across the systems, you are trying to carry out this holistic optimization. Of course, as Michael, as I can imagine, when the domain or the scope of your optimization objective elevates, I suppose the complexity, the challenge.
That's
Please tell us more.
That's exactly it. So people have recognized early on that as someone, I cannot remember now exactly who it was, but I quote them, they say the problem lies in the interfaces when they were talking about systems or systems of systems. And in fact, it's a challenge that can be turned into an opportunity when you utilize optimization, because not only you are accounting for the interactions and these interactions are not well understood at the beginning, but through optimization, you are counting for them, and not only you can learn more about your problem, understand how these interactions impact or influence system level optimality, but then you can also use them to your advantage. So you actually try now to, how do I now that I understand the interactions, or at least I can capture their impact, how do I use it to my advantage to improve the system level optimality of a system, right? So, and of course, the complexity there is that you have very tough numerical optimization problems to solve. And the general remedy is to divide and conquer. So, and again, this follows the systems engineering paradigm, right? It's the downhill of the V.
Yes.
You start to decompose. but then this is an artificial decomposition. So in systems engineering, then you start the integration, then you go uphill the V. But sometimes you stop at the end. Well, what we do in optimization, we actually iterate.
Yes.
And we are, because we know that we have artificially decomposed the system down to a level where we can understand it, optimize it locally. But then we have to make sure that all these artificial decompositions that we have made are also accounted. So we need to put them back and integrate them together and make sure that we have consistency among all these parts that we had separated. And this is the complexity that kicks in, because these are not easy problems to solve. Mathematically, if you like, you can think of them as equality constraints. Right?
Yes.
This has to be equal to this, and this has to be equal to this, and this has to be equal to this, so they can be integrated. But treating numerical equality constraints numerically is extremely hard. So you have to come up with strategies to relax, as we say, these constraints.
Yes.
And try to drive these consistencies down to a small number as possible, ideally zero, even though sometimes it's not possible. But again, some people sometimes confuse that if you're not able to drive all these inconsistencies down to zero, you have failed. No, in fact, you have succeeded in understanding where the problem lies, because you can see where is the problem, which of the consistent constraints cannot get satisfied, and then you can investigate why. Is it because my design space is not big enough? Is it because the problem is too tightly coupled? Can I come up with a different solution? In fact, you can even impact system architecture that way.
Yes. Yeah. Wonderful. And I agree with you. It's kind of, you talk about this, this kind of, I would call it, iterative, right? Iterative, improvement, right? So speaking of that, of course, you mentioned, I think optimization, particular optimization for design, essentially you are basically linking the design space to the performance space. And in between you have the design. Of course, you have all this optimization. So, Michael, so in all these practice, and I feel, I don't know, probably technically, probably kind of the optimization algorithm part, when you are dealing from the design to the performance space, it probably, the algorithm part probably becomes relatively easier in comparison when you explore something which is unclear to you, the design space versus the performance space, even the stakeholders. What performance measures do they really care about? So now putting in the context of, design space, optimization algorithm, and performance space within that. And I want to discuss two things with you. One thing is that when we are doing this kind of optimal design, we try to achieve optimality. But all these designs, they will be used, the product will be used in the future in the uncertain, the kind of either context or the use cases. So for that, I'm going from optimization to, do you go to robust optimization to deal with, how do you deal with uncertainty?
So, and the thing is that it's a part of requirements management, right?
Yes.
Because over time, the requirements will change, and the trick is, can you, especially for products or systems that will be used with very long life cycles, how can we design them so that can be adapted to satisfy new requirements? Or sometimes the requirements doesn't change, but they wear, right? So they wear out, so they need to somehow be reinforced to satisfy requirements. I'm talking about the structural integrity of components, for example, in an air engine. So, and here's where my philosophy, if you like, about
I want to know your philosophy. Yes.
So I'm not alone, but I subscribe to this, and I'm not saying that this is my approach, but I subscribe to this approach. I adopt this approach. I think that optimization is not going to give you one single answer, at least not in engineering design. Optimization is a vast field, and there's tons of other applications where optimization can give you a crisp answer, and that's it. But in engineering design, because of the uncertainties you mentioned, because of the fact that we are rarely in the position to really formulate the entire problem. We sometimes formulate only some smaller problems that we can actually tackle, but not everything. We cannot consider absolutely everything in the design. Take about, for example, the optimal design for an aircraft. I have worked with aerospace and aeronautical airframe manufacturers, and when they start to develop a new aircraft, they cannot formulate the entire problem in all its details completely and start from there and do it. They do it in steps. They start at a very abstract level, and then they go into more detail and more detail and more detail and more detail. And still, it's extremely difficult to capture everything. So it's about how you formulate your design optimization problem. Then it is how you model it, because we all know that the models are all approximations.
Yes.
And of course, then the uncertainty also kicks in. So I believe that optimization is a tool to generate sufficient, hopefully, and adequate quantitative information that will support the systems engineer or the design engineer in their effort. Because, like you said earlier, and I'm really glad you mentioned it, and I didn't have to mention it myself, design is a decision-making process. Right? So, as such, it is subjective.
It is. Yeah.
So, but we're trying to minimize or take out as much subjectivity as possible by providing information to the designer. And we have to also remember the designer deals with vast design spaces, like you mentioned, both in dimensionality and in size. And they also deal with vast performance spaces, the functions of interest, right? What all these objectives and the means to compute, if you're talking about computation, the metrics of performance for different designs. It's a very, very complicated process. Complexity that we talked about earlier.
Yes.
So optimization is a tool there. It's just supporting. But at the end of the day, no one, in my opinion, in my humble opinion, can claim that this is the optimal design. No, this is just one good design for what you considered, what you modeled, how you modeled it, etc., etc.
Michael, thank you so much. I really appreciate, and also I agree with you that optimization is a tool to generate information or even better insights.
Yes.
Right.
Right.
Yeah.
Exactly.
So for that, I want to probably kind of expand a little bit because so far we talk about design, and you and I were both engineers. Well, engineers design things. We're best we are designing some products. But as you and I work with in a lot of in our research project, and we realize actually the system that we are trying to design, it's not only just a product. It could include human beings. It could include institutions. So as such, I would like to go from like the product design to the system design.
Right.
For example, so when we go from a product design where you say, okay, these features of a product, their design space is X, Y, Z, X1, X2, X3. We can try to optimize these things and to even in multi-object optimize the Y1, Y2, Y3. Want to optimize those things.
Right.
And I think you mentioned earlier, the decision has a lot of subjectivity in that. So when we move from a product design to a system design, and particularly, for example, in your role as the associate dean, right? You're managing, it's basically it's a social technical system.
Right. Correct.
It's a social technical system. So do you have any thought about any philosophy of not even say optimization, but improving, a social technical system, probably using some of the tools and the paradigm of thinking that you've been practicing?
It's a very interesting question, and in fact, I know I'm not an expert in this area, but I know that there is a lot of active research work on these socio-technical systems. I cannot claim that I understand them fully, and I have not invested any of my academic time to study them. So I can only talk empirically. And the lesson that I have learned is that people will collaborate if and when they want it. So I'm trying to support all the organic efforts, if you like, of people coming together in multidisciplinary teams from different disciplines to improve this system design efforts that we have. So not just consider the engineering aspects, but bringing in other aspects. There have been efforts when I was at the University of Michigan. I was not involved in these efforts, but there was a big program in design science that going to bring in business aspects, psychology aspects, arts. And that was called the design science program. And it had this objective to how we can look at this system design process holistically, not only from the engineering side. And again, like with all the grand challenges that we have nowadays in terms of engineering, we have to understand that they cannot be solved by 1 or 2 or 3 people. They're going to need big, really big teams that have to really cooperate and collaborate well to solve them.
Yeah, I agree. So, and also I think earlier when you talk about, and it's kind of like optimization has its own limitation, for example, due to, for simply one aspect, you need to know all the details, all the specifications, all the specifics to be the input. So, your optimization model can only do as much as, the details of your input.
Right.
So basically where I'm heading is that because I noticed that you do digital tuning. It's because I feel probably, is that some kind, because is digital tuning some kind of, some kind of solution you are viewing kind of getting better characterized with all the detailed information so that on top of digital tuning,
yes,
you can add the brain there.
Yes, I'm not sure. I'm not sure yet. I have to admit, we are only now getting active in digital twin research, and this is my motivation. I have always, in my career, I have considered problems in an offline fashion, if you like. For example, I was trying to design the system and optimize it, and then it would be in operation and it would work, but I wouldn't interfere afterwards. So I had if you like, a static problem.
You get it born,
right?
And then you
right.
you let it go.
But the way modeling plays a very big role. How we represent the systems that we're trying to design and optimize, and the modeling paradigm has been shifting, right? Just like systems engineering went to model-based systems engineering, and now it becomes digital engineering.
Yes.
So the same way with models, we had static small models and sometimes surrogate models of models, meta models, and then we shifted to adaptive models. And now the digital twin, at least in my understanding, what it does is almost converging the virtual model, the representation of the physical system, and the physical entity into a synchronous time dimension. In other words, that's why I think that's the motivation, at least my explanation, the motivation of the schematic of a digital twin now being the Möbius band, this infinite band, that the two actually will converge to coexistence, and you will be in real time. I don't know how else to explain it. You'll be feeding information from the virtual model to the physical model and back.
Yes.
And the two will almost become
twins.
like, yes, exactly.
Yes.
So this is what motivates my research in this area, because I think we're shifting from this from the engineering
Static to dynamic.
Exactly.
Yes.
Yeah, very well articulated. Yeah.
I can see that, and I can see that it's really it's kind of and I mentioned earlier, so you work before you design a product and you let it go, but now the product will evolve, and then through that process, the product, including the service it provides, can actually benefit from your optimization or any kind of techniques being applied in a real time. Speaking of this, you can see that Michael, being an established researcher, but you are continuing to see new challenges and explore into the new areas. So at 2 levels. at the society level, what do you see as, all these key challenges that are coming upon us? And then, of course, I think that at the society, and then within your research community and also within your own research, you also probably see some challenges and you want to conquer. Of course, probably I believe that you want to conquer some research challenge in your communities that will have very good implications for the societal challenges. Yeah. So what's your view about these kind of parallel challenges and what is your approach and plan?
Yes. So I don't want to seem like a wise guy. We all know what are the big societal.
This is a conversation.
We
can talk about that.
So the challenges that we face as a society, they're ground engineering challenges and science challenges like climate change, the energy question, the greenhouse gas emissions, and on. These are things we know. I mean, and they're all very well documented in the UN sustainability challenges and goals. From the societal point of view, I'm a little bit old-fashioned, and I'm trying to be not skeptical, and I'm not trying to stop progress, but I'm trying to make sure that we do take a pause and think.
You want to be cautious.
Right, cautious about the very fast advance of artificial intelligence. There's no question that it can be extremely beneficial, but things change a little bit too fast for my taste, or maybe I'm just old-fashioned. And I can see it because the new generation is different from my generation. They have grown up in different conditions with different tools. I had my first smartphone 12 years ago, and now they are born with smartphones, right?
That's right.
So it's a very rapid revolution, and I'm just trying to make sure that we do things correctly as we develop tools based on these emerging technologies, and as we apply them to very, very tough problems that people took decades before to study. And now this almost seems to be obsolete, to become obsolete. Like, when we're shifting from learning about our world solely through data, while we used, we needed centuries to develop understanding of physics, right? So I'm more for a balanced approach.
Yes.
Right, and more perhaps like in the as an investor analogy, not put all our eggs in one basket, right?
Yes. Yeah. Also, probably somehow similar to even when you try to explore or try to exploit optimality, but we need to take a balanced approach to optimality.
Right.
Right. It's speaking of AI, I think you and I were probably the same age group, and I think we're in the same boat. And I feel that it's, of course, you mentioned, we want to study, make sure that things go in the correct direction. So, but is that the speed or the direction that scares us?
If I had to intuitively respond, I would say the speed.
Yeah.
Because the direction is something we can always somewhat control, right? Well, it's a very interesting question. I never thought about it this way, but intuitively I would say the speed and the willingness we have to jump into something very quickly and implement it and adopt it, perhaps without studying too carefully or considering more conservative alternatives.
Yeah,
But it's very interesting question. I will probably need to think about it more. Maybe I'll change my mind and my answer.
Oh, sure. This kind indeed. It's kind of. I thought about that as well, because it's kind of. Anyway, we're off topic, but I think this is a conversation. Think about the Big Bang, and when the Big Bang happens, all the objects, they are basically going.
Yes.
In all the directions,
Yeah.
and there's no direction that is wrong, and there's no direction that is right.
Right.
But it just happens.
Right.
So in that sense, and then now we're talking about, as you said, you got your smartphone maybe 12 years ago, and now they're born with these smartphones. And the hell knows which directions, all the future, but the future generation where they're going and what things will make them happy.
Right.
Maybe the things in the future make them happy. To us, we feel, oh, that's really scary, but
Yes.
they will just take as norm.
Absolutely.
So
Absolutely.
this kind of thinking kind of got me to feel that I feel it's really, I think the shapeability of a human brain and also the resilience of human being. I feel these two things are, and also diversity.
Exactly. And
Yes.
its huge capacity to adapt.
That's right. I feel that
It's a survival tool.
Yes. Yeah. So in that sense, because kind of what we think is correct today or wrong today, right? Yeah. Decades later, right? Yeah.
I agree 100% with that. It's a very good point.
Yeah. So now, sorry, coming back.
Yeah.
In your research area, I know that you are in this kind of derivative-free optimization and also Bayesian optimization, particular computational engineering, and I feel that Michael, the advancement of computer science and computational engineering, I feel that added so much power to the optimization, right? So, and with all this technology advancement, and of course, in optimization field itself, and even in your computational engineering design, there are some challenges. So what do you see as some challenge in your field, and that you want to tackle?
The obvious one that my research group is already starting to be active is everything that is under the umbrella of artificial intelligence. So, machine learning. How do we capitalize on the very rapid advances, and how do we capitalize also on the availability of big data to improve our optimization methods and techniques? Well, that's the obvious part. And of course, again, I repeat that we need to be careful understanding how they should be used appropriately.
Yes.
Right? So because when I have a general adversarial network giving me thousands of new airfoils that almost look the same, and I have to look very close, but physically they give me very different responses. I have to understand how will I train a designer and an engineer to use this information and use these results that generative design, for example, will provide. But there is another area that I'm not active yet, but I'm following very closely, and that is making also very, very rapid advances, and that's quantum computing.
Yes.
And the thing is, I'm not going to get active in quantum computer research, but I think that it is very likely that it will still happen while I'm active in research in my lifetime. And I think that I and my group will have to be prepared for that, because this is going to be a disruptive computing paradigm. And we're going to need to understand how will we be able to transit from one classical computing paradigm to the quantum computing paradigm when it becomes, its technology readiness level is sufficient for us to use it as a mainstream tool or mainstream computing platform. And because we will not be able to just translate and transfer algorithms and methods, it will require complete rewriting of codes and complete new development of methods that will be based on numerical truths. At least that's my understanding. So I'm trying to get educated in this area, and I see already that there's been activity, there's been results. There's a field called quantum optimization, where they're actually already presenting results of how quantum computing based optimization will work.
That's great, Michael. So this kind of give me I just want to, since you've been following this, that got to me, one point is kind of, quantum computing for OR, for optimization, and then also OR for quantum computing. I feel, these two things can be, they can be going parallel. But when you think about it in that way, Because to me, I always feel like, mathematics and all these optimization, models and these techniques, to how closely coupled are, on one hand, mathematic optimization, all this, optimization methodology and the techniques, and on the other hand, the computing power. So how coupled and how reliant? Because I feel that, for example, and even for quantum computing, when the quantum computing happens, and even if people are going to use quantum computing to do this optimization, but I naively assume that all these kind of mathematical thing, unless, for example, the quantum computing will revolutionize all this mathematical side, that kind of impact. Are you talking about this kind of aspect impact, or are you talking about, okay, quantum computing will be not replacing this existing kind of, it will expedite?
That's what I need to find out.
Oh.
And maybe it's been investigated already, but I don't have the answer to this question yet. That's what I'm trying to find out. But there's definitely a very tight coupling between computing paradigm and numerical optimization.
I see.
And in fact, the one, so it's almost like a coexistence, right? The one has advanced the other.
I see.
Let me give you a very simple example of what I mean. The very early, if we have time.
Oh, yeah, we have.
The very early optimization methods in the previous century, the early previous century, 1930s, 40s, were derivative-free optimization algorithms.
Yeah.
Right? Then, of course, theory went into gradient-based optimization, and it was developed to a very mature level. It's the theory is beautiful. It's complete. It's it's excellent. It's an excellent mathematical framework for optimization. But that was done because back then people were still looking at analytical problems.
Yeah, closed form.
Exactly. As computing power, as computation discipline was developing, people started developing computational models. And then in the optimization community, they started realizing that for many of these computational models, we don't know if gradients exist theoretically. And even if they do exist theoretically, we don't know if we can compute them or approximate them adequately with reasonable effort. So this motivated the community to go back and research derivative-free methods, because the computational models were getting so advanced and so complex.
Yes.
And so you see how the one was driving the other.
Yes.
And it's almost like a chicken and egg thing. It's like computational power and computational ability increases, but so does our modeling ability.
I see.
And then you're trying to catch up.
Yeah, I think thank you for telling me that history. It's kind of, you say, before the 30s, and it was kind of derivative free, and then we have derivative based, and then when the computing power kind of got developed, somehow this computing power somehow revolutionized optimization and then brought back
Exactly.
right the derivative free, but in a totally different paradigm.
Yeah. And I'm talking about rigorous derivative free optimization algorithms. Yeah. I'm not talking about heuristics, which are very useful too. Yes. But I'm talking about research.
Rigorous.
Yes, exactly. Yeah.
Wow. So I know that you're going to be given a talk later, but maybe I can kind of pick into a little bit. So now in your area of research, what issues are at the frontier in your research community, and what issues are you using your power to tackle? So
right now we're looking at how to manage efficiently and effectively multi-fidelity models. So in other words, as we navigate and explore design spaces, we're trying to quantify the trade-off between predictive capability and computational cost. And depending on when we are in the design space, we're trying to figure out what is the, in our terminology, adequate model that I could be using in this area. I don't have to have, depending on how much fidelity I need and how good my models are. So this is multi-fidelity management, and it also translates to Bayesian optimization, where you're trying to deal with ensembles of models that are being adapted as you visit new areas of the design space. And it's always a game that you're trying to work with lower accuracy but also lower cost models to get good promising candidates. But then in our strategy, at the end, we always validate that with the highest fidelity model we have.
Yes.
But it also causes a lot of computational time. But when we get these answers, then we can adapt our models. So that's the Bayesian optimization paradigm. And now, in this ensemble of models that we're considering, we are now looking also at, we're trying to follow the trend of machine learning and deep learning and all these models that become available that some require, and we're trying to also address the necessity for large amounts of data for these models to be successful in their prediction. And we're also trying to solve the what is known as the cache problem, which is the algorithm selection and hypertuning parameter problem. In other words, again, which of these deep learning or machine learning models should I be using? How will I tune its parameters to give me the best performance? And how will I do this while I'm actually doing the optimization? It's a very challenging problem, and this is where we're getting active into.
Michael, I think that this is so basically optimization for optimization. Right. You want to achieve.
Yes.
Right. I agree with you because you talk about the multi-fidelity, and I told Caesar because that again gets to because it seems like you're also a member of this. I think this group for research in decision analysis, because I feel the reason I'm mentioning this because the decision optimization is done depending on what kind of decision you're making.
Right.
Depend on the decision level. Depend on the level of fidelity of the decision.
Right.
And your optimization can be at different fidelity levels.
Right.
And then, of course, you need to decide exactly what kind of fidelity level will be the minimum cost.
Exactly. And somewhere in all these methods, there's always the human factor entering and the subjectivity of the human factor. Right? There's always something like, what is the adequate threshold? Sometimes we say 95, 99%. Well, why is it 99 and it's not 98.7? Right? We cannot get completely away from that. Maybe one day. But and of course, there are also research areas that look into automating this and having the systems decide for themselves what are these parameter values that we sometimes semi-arbitrarily pick. Yeah.
Yes. So, Michael, as we get, I think closer to the end of our discussion, and I really enjoyed this. So I think I want us to talk briefly about education because, and I think when you were, introducing yourself briefly about your education, of course, you were born in Greece and you received, German education, and then you went to take a University of Muni, and one thing I think you did not particularly plan your career, and it just seems kind of.
It's correct. Yeah. You realized this correctly.
Yeah, yes. It just kind of played out, right?
Yes. So there were also different times because the amount of information back then was at a very low level. The amount of information that young folks have today is unbelievable. I mean, we did not have the internet back then. We did not know which university to go to, what to study, who is working there, what they're doing. It was almost impossible to get all this information. Right? Yeah. Sorry to interrupt.
Yeah, I agree with you.
But I think it's very important to realize.
Yeah, I agree with you. But yet somehow, Michael, if you look at it in a different way, somehow, even though at that time we did not have that kind of luxury of the data and information like our future generation has, somehow it was also fortunate.
Yes, I believe in that. Yes,
right, because I think nowadays, because I think when the children, when they're not at the age of making decisions and all this information coming to them.
It's overwhelming.
Yeah, quite overwhelming. And even you see that, when we advise these undergraduate students coming to Cornell or coming to McGill, they're already 18 years old and they still don't know.
Yes.
Right, so somehow, right, I was the same as you. We just move on, and whatever came to us, and we just keep working on, and things worked out.
Right.
And actually, that way, I think probably in comparison to these current generations, yes, we were lacking information, but somehow we did not have a lot. We did not have a lot of unnecessary stress.
Right. And pressure. Yes.
Yeah, and pressure they have today.
You're absolutely right.
Yeah. So for the education, but I think it's kind of the vision that you have, of course, all the the research that you are proudly carrying out. How are we going to be able to train and educate the future generations that you feel that they will have,
We mentioned
yes,
grand challenges before.
yes,
And I mentioned that I think that these grand challenges can only be solved by large collaborative teams.
yes,
So, in the future education needs to keep investing. It's already happening in interdisciplinary programs and teaching young engineers and scientists that the key to success will lie in successful collaboration. So they need to understand from early on that they're not going to be solving system problems by themselves. They're going to be collaborate sometimes in very large teams. So it's going to be important for them to get used to techniques for communication, for cooperation, and teamwork. Extremely important. Also, they will have to have a more broad view of technology, society, the problems that we have, etc., etc. And in that sense, if I may mention something that is very close to my heart, and I'm very, very happy that I was involved in. I was on sabbatical in France 6 years ago at what is called now Centrale Supélec. It used to be École Centrale Paris, and it was fusioned with Supélec, which is their Grande École for electricity, and they are belong now to this new big Université Paris-Saclay. It's a very big conglomeration of Grande École which are top-notch institutions in France, higher education institutions, universities, research centers, etc., etc. Long story short, I spent a sabbatical there, and I saw that there was the conditions were ripe to create a joint, not dual, a joint international program together. And again, long story short, we have created an what we call a global bachelor of global engineering that recruits a cohort of about 80 students for the moment. We're in our second year of operation. 80 students. 80 students.
Wow.
Worldwide. For now, there is a very strong French connection because of McGill being in Montreal and Quebec,
Yes.
and the school being in France. But these are kids that have many times come from all over the world because their parents live all over the world. And we are trying to recruit students who think globally and have a broader vision of the world, not just a local vision. And they spend 2 years, the first 2 years they spend it in Paris at Centrale Supélec, where they get the traditional generalist French approach to education. So they are trained by dedicated professors in mathematics, physics, biology, chemistry, philosophy, languages, sports, of course not equally distributed, but without any specialization. So they get 2 years like that, and then they move to McGill for 2 years of specialization where we offer them strings. Like we have a breadth string where you can shop around, but we have a mechanical, electrical, computer science, data science, entrepreneurial, you name it, civil. And of course we are in the second year of operation, so we have not graduated anyone yet. So we have the first 2 incoming classes, and we're really looking forward in 2 years to see the people who will graduate, how they will go on. Maybe they go to graduate studies, maybe they go on to global enterprises. We have also a lot of other things going on in between, like internships, social internships, engineering internships, summer schools, etc., etc. But we're looking to educate young engineers, in this case, who have a very broad vision of the world, want to attack global challenges.
I like that so much. I was even going to ask in kind of the language used for these instructions, is that French or
English?
English.
Even in France.
Okay, that's
even
great.
when in the first 2 years in France, it's English.
So you get that these kind of 80 students are coming from every part of the world. I think this is wonderful, and I think our world, we need many more of people that have the global view.
Yes.
And I think that's so important, and particularly I think at the end of the day, even for us, the lifelong learning. You and I, we know some mathematics, we know some algorithms, but I think in the end, it's really what determines our own lives and also our contribution to the society. I feel it's really those kind of global view, those like a philosophy, the values we hold. Because otherwise, kind of, if instead of becoming a mathematician, you could become a electrical engineer or something. But it's really all the skills can be different. But it's really I think the view the
But
value.
it's a very difficult thing to accomplish, because you really need to be careful about this breadth versus depth trade-off, right?
Yeah, I agree. Yeah,
We neither want to have. It may not be politically correct anymore, but back in my years when I was studying in Germany, there was a German word called Fachidiot, which means an idiot who knows everything about a very specific thing. It's a German word. Hopefully I can still use it. But we also do not want people to know nothing about everything, right? So it's something that I hope we can manage well, how to trade breadth versus depth.
Yeah.
But again, if you collaborate and you bring people of different skill sets and different knowledge, then that is probably a self-correcting system.
I agree, and I think it's kind of the word comes back to balance, right? Balance. But I think from an individual point of view, it's kind of it's I think that somehow the society is so cruel in a way that due to economic development and also the jobs and the kids early on, they have to say, okay, should I specialize in this area that has a better job market when I graduate? Because that's kind of generalization versus specialization.
Right.
From a jobs and from a society economic point of view, I think economists, they probably already figured out the more specialized people are trained, the more efficient probably. However, I guess from an individual development point of view, I believe the more exposure an individual has, the better off for that individual.
Exactly.
Yeah.
It's almost like the analogy of traveling, right?
Yes. Yeah. Mike, I know our time is up. It was such a great pleasure.
Yes, the time flew. I'm sorry the time is up. I would have loved to talk about more. It was a real pleasure. Thank you very much for setting this up.